It'll seem like it's just going to seem like this is a useless topic, right? Until we get to a point where it's not, right? So a differential or a differential form of an equation is something that's in the form of dy equals something dx, right? That something would be the derivative of a particular function, all right? So what do we want to do? We want to take the derivative of a given expression. Oh, that's the wrong marker. Equation. So dy dx would be equal to 5x to the fourth plus 37. All right, what we have here is known as a differential equation. All right. The only additional step to this would be multiplying both sides by dx. So I'd end up with dy equals 5x to the fourth plus 37 dx. All right, so I'm multiplying both sides by a dx. That gives us the differential form. All right, so we have a differential equation, and then the differential form of a differential equation, which is really just solving for one of the d's. So either dy in terms of dx or dx in terms of dy. Right? Traditionally, we go for dy in terms of dx. If I wanted to, at this point, I could find the antiderivative and work backwards, but that would defeat the purpose because we just found the derivative. Right? But that's all you would need to do for any of these questions. Take the derivative and then multiply both sides by dx. So again, seemingly a useless topic. Like what? Okay, cool. We took a derivative and all we did was we just moved the dx part to the other side. Right? There is value in this, and the value comes from the fact that dy actually is something, and so is dx. Right? We're talking about a change, but a change on a minute level. So on a minuscule level, a smidge of change in the y direction is related to this, basically this relationship, this product of the expression 5x to the fourth plus 37 and whatever the smidge of change is in the x direction. So what we created is some kind of proportional relationship. It tells us that the product of these two things will give us a value that represents the smidge of change in y. Right? And so, in theory, that sounds like, all right, well, what is it really telling us? We're just multiplying two things. If I were to give you an arbitrary sketch, because I know generally what a quartic function looks like, but I don't know what this particular one would look like, and I don't want to go to the calculator. So it's some W-shaped graph. All right. What it's telling us is that on a very, very teensy tiny little level, you have a point. That point is going to have some height. All right, let me get an axis here. All right, every coordinate in space is an x value followed by a y value, x comma y. So in this case, it would correspond to x comma 5x to the fourth plus, I already forgot, 34? 37. All right, so this is the y value here, the 5x to the fourth plus 37. So that would actually be the height of the point, 5x to the fourth plus 37. All right. When you multiply it by dx, what you're doing is you're multiplying it by a dimension that represents a minuscule change in x. All All right, so 5x to the fourth plus 37 multiplied by dx would give you this area. A very minuscule area, very teensy tiny. That's the whole, and that's why I zoomed in so much, because it's supposed to represent the tiniest little smidge of area underneath this curve. All right, so what dy will actually represent? That differential form, the dy that emerges from that, that's going to be the area of a rectangular region under a curve. All right, so that's a little bit of the theory behind it. Now, it's only going to give me that little teensy tiny smidge of movement in the x direction. All right, so it's going to give me just a tiny sliver of rectangle. So the question would be, well, what if I wanted the entire area underneath the curve? You know, over a large interval. What would I do? Well, I'd have to figure out the area of each rectangle for every possible little smidge, right? So I'd have to have particular x values and dx values, right? And then I would have to add all that up together, right? The good thing is there's a process called integration where you actually integrate all those areas. So we're going to collect all those areas and put them together. It's actually a very simple process, but it involves taking an antiderivative, right? So that's kind of where we're going with this. So what I wrote here, step 1, step 2, seems completely, what are we doing? We're taking the derivative and multiplying both sides by dx. You know, if I were giving a quiz on this, yeah, everybody would get this question right? But it's the underlying meaning that's really important, because that's going to drive the learning from here on out. All right. And also there's some things that we can do with this that are pretty cool. So you can read the blurb. Differentials are variables that represent change. So we can actually estimate change with just our knowledge of differentials. All right. So if we're talking about dy representing some minuscule change in the y value, then we can use that as an estimator of a particular change. It could be any variable. We could be relating temperature and time. We could be relating speed and time. You know, anything, any two variables. All right? And so these techniques allow us to figure out something called absolute change, which would be the real change in a particular variable for some change in x. The other possibility would be an approximate change, right? So that's where the differential concept comes into play, right? So this graph really illustrates that, but it doesn't really make much sense until you start diving into the calculation. So I'll come back to this. All right, so our absolute change formula, delta f of a plus dx minus f of a. The estimated change is a much simpler formula. Right? In fact, it's the differential formula, differential form of a differential equation. So if we know this piece of information, then we could actually come up with an estimated change. The approximation error is huge, because if we can determine that there isn't much of a significant difference between the estimated change and the absolute change, what that tells us is that we can use the easier formula to come up with an approximation of whatever change there is. The first couple of examples just deal with plugging and chugging, and then we get into some contextual situations. All right, so we're going to find the absolute change. It says f of a plus dx. All right, so they gave us an a, they gave us a dx. So let's figure out that part first. That would be f of 0 plus 0.1. So f of 0.1. All right, so that's taking a 0.1 and plugging it into your original function. So 1/10, 1/100th, so 0.01, 0.21? You just pop it in your calculator. Just at some point, let me know if I just screwed that up.
Where did x squared and 2x go?
We're replacing the x with the 0.1 in the original function.
Okay. But with an f, where is what's...
Function notation tells us that whatever is inside the parentheses is replacing the variable in the equivalent function.
Okay, so the f is just function notation, that's what I mean?
Yeah. Alright. So then f of a, alright, so that's f of 0 in this case. That's going to be equal to 0. Alright, because if I replace every x in the original function with a 0, it's going to 0 out. Alright, delta f is really just the difference between those two numbers. Alright, so delta f, capital delta, is going to be 0.21 minus 0, which is going to be 0.21. Alright, and so what that tells us is the change in the function, sorry, it tells us the change in the function over this interval. Alright, so if we're looking at a graph of this, we're only looking at the graph that extends between 0 and 0.1. So actually I can show you that real quick. So x squared plus 2x. The x min would be 0. It's going out to 0.1. Just leave that at 1. And then I'll just let the calculator do the thing. Alright, so if you were to trace along this, you can see it's all values between 0 and 0.1. Right? So very minuscule change in x. Right? But if I were to test, for example, the starting point, I could do a value at 0. It gives me a 0. I could do a value at 0.1. It gives me the 0.21. Right? So all this technique is doing is finding the difference between the y values in the beginning and at the end of your interval. Right? So in terms of calculation, it's not too bad. It's the interpretation that has meaning. Right? But in this case, what's the interpretation? There's no context. So I don't know what this parabola is referencing. Right? So there's no value in trying to determine what this would mean other than just a change in height. All right. The estimated change. This is going to be an easier thing to do. So the estimated change, df, would be equal to f prime of a times dx. So that means that I need my f prime of x. So the derivative of the given function, 2x plus 2. If I do it at the given a value, which was 0, it's just going to give me a 2. All right, so df would be equal to 2 multiplied by the dx value, which is 0.1. All right, so 2 multiplied by 0.1 is equal to 0.2. Which is not too far off of the absolute change. Right? So if I know that this is the real change over this particular interval, and this is what I would get using an approximation technique, I walk away from this thinking, well, the approximation technique's pretty good because I'm getting an answer that's pretty close to the correct answer without having to do as much work. All right? When you're evaluating functions, it all depends on how difficult the function is to begin with. You know, if you're dealing with something that's polynomial, it might not be too bad. But if you throw in some trigonometric function, you know, a log function or something like that, working with the estimated change is going to be significantly easier. Right? So the approximation error is really just the difference between the two. the absolute distance between the two. Which, in the grand scheme of things, is pretty insignificant. So the second example is along the same lines, right? But then you get into a practical situation. All right, so I'll leave number 2 for you, but I'll do number 3 with you. All right, so the radius of a sphere was measured to be about 84 centimeters with a possible error of 0.5 centimeters. Use differentials to estimate the error and calculate the surface area. So they're giving us surface area, which we'll write as A equals, instead of S, 4 pi r squared. If we're going to use differentials, it would require us to differentiate, aka take the derivative. Right? So dA dr, instead of x and y, would be equal to 8 pi r. All right, you can write it as A prime if you want. Doesn't make a difference. All right. So it's really, again, just a differential form. So basically, I'm just kind of inventing the formula as we go. Because if I multiply both sides by dr, I have the estimated error, estimated change formula just in particular variables related to this problem, right? So what I'm looking for is an estimate of the error in calculated surface area, right? So it's a multi-step thing because I'll actually have to figure out the absolute change, but for now we could figure out the estimated change. So they're telling us that the radius is 84, so I know what r is. A possible error of 0.5, so they're telling us what dr is. All right, so when they give us an error in a particular variable, that's the change that you're allowing. So this is r, and this is dr. All right, because really, if you think about it, we use the term change, like change in y over change in x, for slope, but really it's a deviation. Okay? It's how far you're moving from a point. So we have 2 directions, x and y, horizontal and vertical. But if I'm telling you that there's an error, that's the same thing. It's a deviation from a point. So I'm allowing a deviation from the radius of 84. I'm allowing the deviation to be 0.5, which is the same as saying the change in r. All right, so the instantaneous change in r. So I could put these numbers in and get my dA. 8 pi times 84 times 0.5. Is that 336 pi?
Yes.
Yeah. So 336 pi, the units would be important, right? It's a contextual situation. 2 dimensions, so power of 2 centimeters squared. Right, so this is the estimated change. All right, so it's creating variation in area. Right, so if I have a change in 0.5 in terms of the length of the radius, that's going to give 336 pi, and you can multiply that out, but that's pretty close to 1,000. I don't know if it's north or south, but it's in that neighborhood. 1,000 square centimeters of error will now be introduced in your area. All right, so just by allowing for a 0.5 deviation in the radius. All right, so if we're off by that much in the radius, it's going to have that much of an impact on the overall area. All right, the surface area of the figure.
Can I ask?
Sure.
I understand all except until the possible error. So the dr. Okay, I understand. Just didn't see you.
For these kind of problems, I mean, it's a little easier, I think, to come up with a visual, because if you really think about it, like just imagine a balloon. If I don't know about 84 centimeters, I guess that's reasonable, but if you blow up a balloon, it's going to a certain particular radius, it's going to have a particular size associated with that radius. Now, if I increase the radius even by a little bit, it's going to have a drastic effect on the overall area. Okay? So you just imagine coming up with a way of measuring the area of a balloon if I blow it up to a certain radius and then get that measurement, so go around the balloon collecting all the little areas, adding them up, and then just blow another breath in there, making it bigger. There's going to be a lot more area to that sphere. So it does kind of make sense that you would have a massive difference when you kick over to another dimension. Right? If you start getting into volumes of other figures, it's less easy to, or it's not as easy to visualize, because, I mean, if you're not familiar with a trapezoidal prism, then you wouldn't necessarily know what would happen to the volume of that if you manipulate the area. But for a sphere, it should be pretty easy. But we do need the absolute change. Right? So absolute change, if you go with the formula, I mean, it's pretty cut and dry. But you don't actually have to go with the formula, because if you understand the underlying concept, which is the area at 0.5 below 84 and the area at 0.5 above, and then subtract the two, then you can do it that way. But you know, it's still early on in the process, so we'll just go with the formula. So absolute change f of 84 plus 0.5. All right, that's the a plus the dA or dx. You know, it's r in this case plus dr. So we'd have to figure that out. And I mean, I can do some mental math, but I'm not that good. So you get that. That's fun. Yeah, it doesn't even matter. So 89727 .02778. Then we would just need the f of 84. So a little copy paste action. Get that. So 8866. Oh, that's not right. All right, so then I would just subtract it here. So you get 1058.717-ish. All right. So our delta F, I'm using F, but it would really be A for area. It really doesn't make a difference. Would be 1058.717 approximately. All right, so this ends up being the moment of truth, because I kind of threw it out there that 336 pi is somewhere near 1,000. So let's see how near 1,000 it is. So 336 pi is that number, right? So our estimated value is not too far away from the actual value. So this is the actual change based off of the 0.5. Okay, so if you have a deviation of 0.5 from whatever your particular radius is, you know, that, when you talk about deviation, you're talking about give or take. So if you're asked to estimate something, you know, most of the time you say, yeah, I think it's going to cost about $50, give or take a couple of dollars. You know, it's the give or take that we're talking about here. So if somebody had to estimate the radius of a sphere, they're probably going to throw a little wiggle room in there. They'll say, I think it's 84 give or take 2 units, give or take a percentage point or something like that, all right? But if you know that this technique, which I think was much simpler, allows you to come up with an answer that's very close to the correct answer with like half the work, why wouldn't you use that technique? All right, so 1058.716.725 minus this. So it's off by pi. That's cool, I guess. I don't remember why that's the case. But the estimation error is approximately 3.14 square units. Which in the grand scheme of things is not a large number. So again, that's the whole point behind it. It's to come up with a more user-friendly technique for coming up with a change in a particular function. A technique that doesn't involve just rote calculation over and over again. All right? And again, I mentioned this before, this is going to tie into the concept of integration, which, when you think about college level calculus, you got really, if calculus is a requirement, it's usually calculus 1 and calculus 2. All right, so this is the transition between calculus 1 and calculus 2. Believe it or not, we actually pretty much finished all Calc 1 already, because Calc 1 is skills based. And the feedback I've gotten from students in the past is that they were more than prepared for Calc 1. To the point, I think I gave the analogy earlier on in the year. I don't know if analogy is the right word, I'm just making stuff up now. But the student who was sitting in their calc class in college, teacher was explaining a concept, I think it was the power rule or something like that, and it wasn't going well. The students didn't understand what was going on. And so the student, my former student, said, "Tap me in," and then taught the rest of the class, and then became the TA for the class. Yeah, and that was his first time taking that course in the college level, so he already knew the material. Everybody that finishes my calc class here goes on to college and gets an A in calc. Right? So that's just the way it is. So this transition will allow you to do well not only in calculus 1 but also calculus 2 if you take it seriously. So your motivation in the second semester, because it's like, I don't have to do any work anymore. Well, it's true and it's not true, because I'm telling you that I'm not going to make you do, wherever I have control over the situation, I'm not going to make you do individual tests, so less work, but I am going to ask you to continue keeping up your end of the bargain in class. The benefit on your end is that it's going to require much less effort in college. Right? So, it's hard to think about the long game, but that is, this time next year, you'll be in Calc 2, if that's the path you're taking, without any trepidation whatsoever. Because you'll be like, I've seen all this before. Right? So that's your motivation. Also, you don't want to get a fear of God letter. Those are fun. One student read hers out in class. The one where it's like, yeah, I know we said that you're accepted, but we're kind of not going to accept you if your grades continue to decline. Because they don't want to see massive drops from the first semester to the second semester in terms of your performance. So if you've typically been an A student and now all of a sudden you're carrying C's, you're probably going to get the fear of God letter. Right? And so sometimes they do rescind the acceptance. That's why they have things like wait lists. So if you got waitlisted, in a lot of cases, one situation is where students have to commit to the school. Another is they have to commit to pay. So if they miss payment deadlines, application's done, right? But the third one, which is the less likely outcome because you're all going to do the right thing, is a drop off in performance. So any of those three things can get you off of the wait list and into the school that you apply to. But it could also take an application that was accepted and make it the opposite of that. Right? So definitely, you got motivation all along the way. Fourth quarter, all bets are off. At that point, I have nothing. There's nothing I can tell you that would make you more motivated than you are willing yourself to be. Right? I can't threaten you with anything. I mean, unless you put yourself in a position to fail the course, I can threaten you with that, I guess. But even still, at that point, the ship has already sailed. You've already committed. You probably have a roommate at that point. So, like fourth quarter, I really can't threaten you with anything. The third quarter, you're still on the clock here, right? So you still got to do your part. But I'm trying to be nice about it and not make you do any more of these bad boys, you know. So I'll do my part. You do your part. All right, and this, as useless as it might seem, you do have to trust me that it is going somewhere that's very important. All right.